Flipped classroom video for Maths A2, Unit 3, Integrating Powers of X. Going to look at the area under a function. And we need to look at some notation. And the fundamental theorem of calculus tells us that we can find the area under a curve by using the antiderivative. Now, if we look at this diagram here, then we're looking at the area in a sort of different way. We can slice it up into rectangles, and each of these rectangles has the height of f of whatever the x-coordinate is on the left of them. And if we reduce their width, we get an increasingly close estimate of the area. If we look at it now, then if we were to add those two rectangles together, that would give us quite a big underestimate of the area. But if we just watch this animation, you'll see the idea. So as the number of rectangles increases, the deficit from the actual area is getting smaller and smaller. Now, each of those rectangles has a height of whatever the x-coordinate is on the left of them, times by our little delta x, which is the width of them. So that means the estimate for the area is the sum of these rectangles, and we use that Greek s there to notate that. Now, if we let delta x tend to 0, then we have that the actual area will be the limit as delta x tends to 0 of the sum of our f of x's times delta x's. And it's a hard idea to get your head around, but if you imagine those rectangles just getting thinner and thinner and thinner, then they would eventually, if we can imagine them going to a width of nothing, they would be the same as the curve. And if you find that difficult to understand or to comprehend, that's because it is. But the idea is that imagine that video that we've just seen carrying on with thinner and thinner rectangles, then at some point it would look like the curve. Now if we zoomed in, we'd still see steps, but then we could make them thinner and thinner, and in the end, with the limit, we would have the area itself. And the way we write this limit is a of x is the integral, that's that sort of s, long s there, of f of x dx. Okay, so as I've just said, we write that limit in that way, and we say this is the integral of f of x dx. The integral sign, as I mentioned, is an elongated s, so for a bit of fun there is an s elongating, and we can see that it ends up looking very similar to the integral sign. And that may help you to remember this is really about it being a sum. So we know that a dash of x is equal to f of x, and so in order to find a of x we need to find the antiderivative of f of x. We know how to do this for powers of x, so we can say, for example, that the integral of 3x squared dx is equal to x cubed plus c, and that's because x cubed plus c is an antiderivative of 3x squared. Using our general rule, we can say, our general rule that we developed for antiderivatives, we can say that the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus c. Okay, now we're going to use examples from a previous video, which was antiderivatives and the fundamental theorem of calculus, so let's have a look at them. The integral of x to the 5 dx is x to the 6 over 6 plus c. And remember, the procedure is add 1 to the power, divide by the new power, and don't forget to add a constant. Okay, the integral of x to the half dx, well, x to the half, the first step is add 1, so that's x to the 3 over 2. The second step is divide by the new power, so that's x to the 3 over 2 divided by 3 over 2. And if we now times the top and the bottom of that by 2, we get 2 times x to the 3 over 2 divided by 3, and there's our plus c. For the integral of 3x to the power of minus 5, then we start with 3x to the minus 5, we add 1 to the power, so that's 3x to the minus 4, and then we divide by the new power. So that's 3x to the minus 4 over minus 4, and that becomes minus 3/4 of x to the minus 4, and again there's our plus c. Now if our function is formed by adding powers of x to get a polynomial, we can integrate by integrating each power separately. So we'll have a look at an example of that, and we'll remember that our procedure is add 1 to the power, divide by the new power, add a constant at the end. So we know that x to the 5 will become x to the 6 over 6 by using our procedure, and x to the 4 will become x to the 5 over 5. So what about x? Well, we know that x is the same as x to the power of 1. So then our first step, we add 1 to the power and we get x squared. And then the second step means we divide by that new power, so that gives us x squared over 2. For our 4, remember that 4 is equal to 4 times x to the power of 0. And so our first step gives us 4 times x to the power of 1. Second step, we divide by 1, which makes no difference, but we've written 4 times x to the power of 1 divided by 1, and then that gives us 4x. And then we must remember plus c. Okay, another example, we have x to the power of 2 over 5 plus 1 over x squared dx. So looking first at x to the power of 2 over 5, we add 1 to the power. Now 1 is equal to 5 over 5, so that gives us 7 over 5 when we add the 2 over 5. We then divide by 7 over 5, but if we times the top and bottom by 5, that will then give us 5x to the 7 over 5 over 7. Looking at plus 1 over x squared, well, 1 over x squared can be written as x to the power of minus 2. That then, when we add 1 to the power, gives us x to the power of minus 1. We divide by that minus 1, and that then gives us minus 1 over x, because x to the power of minus 1 is 1 over x, and the minus 1 makes the whole term negative. And then, of course, again, we have to add c.